Okay, as you see here, this example is to find the area bounded by f of x equal x squared minus 4, the x-axis, and really the vertical lines x equals 0 and x equal 2. We're saying the area from an x value 0 to an x value 2, and of course the x-axis, that's the idea of under the curve, isn't it? So we might get started and just remember that formula and say, okay, here's how we calculate such an area. We'll integrate, and the lower value of x is 0 and the upper value of x is 2, and so we're going to integrate from 0 to 2. And of course it's, remember, f of x times d of x, or with respect to x as we're reading it here. So as we begin to calculate then, of course we would actually replace f of x with the x squared minus 4. And now it looks very normal, so we're kind of used to the setup, what we're going to go through. And so we'll do the indefinite integral of x squared minus 4 in our head. That will be 1/3 x cubed minus 4 times x. And so we'll evaluate from 0 to 2. And so that means, of course, we substitute a 2 in first. Remember, the 2 goes in first, so that's 1/3 times 2 cubed minus 4 times 2. And then from that, we subtract what we get when we substitute a 0 in for x. Well, when we put a 0 in for x, we get 1/3 times 0 cubed minus 4 times 0. And we're kind of fortunate here that everything over on this right bracket is 0, so we're really just subtracting 0 there. So this ends up being, let's see, 1/3 times 2 cubed. 2 cubed is 8, so that's 8 over 3 minus 8. And as we calculate that, let's see, we need a common denominator, so that would be 8 over 3 minus 24 over 3. And of course that gives us, negative 16 over 3, doesn't it? How can that be an area? We can't have an area that's negative, can we? So what does that mean? Well, this is what it means. Way back up here. Oops. What we always need to do is to sketch a graph. See, we didn't take the time to sketch the graph, did we? And so we really don't know what the heck it is we were doing. We really don't have an idea. We just worked with a bunch of symbols and numbers. Let's sketch the graph of the function f of x equal x squared minus 4. Now, if we sketch that graph, that's a parabola again that opens upward, isn't it? Now this time, I'm going to sketch a little differently. This time, it's actually goes down 4 units. 1, 2, 3, 4. There's negative 4. Let's say 1, 2. Let's say here's negative 1, negative 2. I know it goes through there. So this graph looks something like this. And you can verify this. It looks something like this. I'm dashing it in because we got to figure out what the heck we're supposed to find. Okay, now we're looking at the area that's bounded by the graph, the x-axis. Well, of course, here's the x-axis, and x equal 2, 0 to x equal 2. Well, here's where x equals 0 is, and here's where x equal 2 is. And it didn't actually say below the graph this time. It said bounded by the graph and the x-axis from x equals 0 to x equal 2. So we're actually supposed to find the area of a region that is below the x-axis. And that can result in what we see here, a negative number. Now the reason that results in a negative number is to think about how we set this up to begin with. When we were doing this, we decided that the area of a single rectangle, in this case, if we think about a single rectangle, let's kind of rough one in here. So we're talking about the area of this single rectangle. Well, of course, length times width. But the problem with the length this time, f of x, see, that's a y value. And in that part of this graph, those y values are negative, aren't they? See, that's the problem, is that y value is negative. Now the width, that infinitely small width, is just still dx, but that f of x, that y value is a negative number there. So we had a bunch of rectangles that we said their areas were negative. Now, so what we're concerned about here is if we have this region that's below the x-axis we're calculating, then we're going to get just the opposite of what we should be getting, because we really ought to be saying in this case that when we do this calculation, the area of the rectangle really should be this, shouldn't it? The height of that rectangle is the opposite of f of x, because f of x itself is negative. So when we integrate, if we were to calculate the area now and we were adjusting this, instead of saying f of x, it would be the opposite of f of x to make sure we have a positive height. And now we can deal with that, because we would end up with the integral from 0 to 2, and f of x itself is x squared minus 4. So we have the opposite of x squared minus 4 with respect to x. And of course, the opposite of x squared minus 4 ends up being 4 minus x squared. And so that's what we need to integrate. Now, when we do, I'm sorry that I've kind of run out of space down here at the bottom. Let me, if you will, I'm going to be sloppy here. Well, let's go up here. Okay. We know when we integrate 4 minus x squared, we're going to get 4x minus 1/3 x cubed. Now, this is what we're going to evaluate from 0 to 2. So first we're going to put a 2 value in, and when we do, that's going to give us 8 minus 8/3. And when we put a 0 value in, we're going to get a 0 minus 0 again. But in this case, we have 8 minus 8/3, or 24 over 3 minus 8 over 3, which is positive 16 over 3 square units. So it came out right. And the reason we made the mistake is we didn't look at what we were really trying to get the area of. So let's continue again. Let's do one more example and recognize that we have other problems that we have to deal with. Well, maybe we'll do a couple more examples. Okay, you can see this problem. We're supposed to calculate the area bounded by the curve, and I'm using y instead of f of x. Y is equal to x cubed, the x-axis, from x equal -1 to x equal +1. So the x-axis is the horizontal line, isn't it? So this is between the curve and the x-axis, and from x equal -1 to x equal +1. Okay, so if we were to start this normally, if we were to start this like we did last time, and said, okay, well now we can just jump right in, let's calculate an area. And the way we calculate an area, we'll integrate from x value of -1 to an x value of +1. And what are we going to integrate? We're going to integrate x cubed dx. See, that x cubed is the height and that dx is the width. And we're adding up infinitely. And so we go along and we can calculate, this isn't going to be too bad to do, because the integral of x cubed is 1/4 x to the 4th. And so that's what we're evaluating from -1 to +1, isn't it? Sometimes when it's just one term, you see I only put half of the bracket. We could put the whole bracket there. And so when we do a calculation of this, we first put a 1 in for x, so we'd have 1/4 times 1 to the 4th power, and then we would put a -1 in for x. We have minus 1/4 times x, which is -1 to the 4th power. And that ends up being 1/4. And -1 to the 4th power is +1, so that's a minus 1/4, and we get a 0. And that's another big fat question. How can we have a curve and have an area of a region that's zero? And it's the same oops. See, it's the same oops that we did before. What does the region look like? You know, what is the region? We need a sketch of a graph. Otherwise, this doesn't make any sense, and clearly, this is not the right answer. Well, not a question mark, oops, an exclamation mark, isn't it? We have no sketch. That's the problem. And so we really don't know how to set this problem up. So the point I'm trying to make is you need a sketch before you start to graph. Now, I'm going to sketch in y equal x cubed quickly for us. I'm assuming that you can do that. I guess you could have with a graphing calculator, worst case scenario, but we ought to know what x cubed looks like. Y equal x cubed. So I'm just going to, like I say, sketch it in. And let's say this is where positive 1 is. And so similarly, this would be where negative 1 is. And say out here is where positive 1 is, and out here is where negative 1 is. And we can find out that negative 1, 1 is on the graph, and 0, 0 is on the graph, and positive 1, 1 is on the graph. But the graph actually looks something like this. Oops. Now, we're interested on the area that is bounded by, the region that is bounded by this graph, but also the x-axis. And so, for instance, between this graph and the x-axis, we're talking about stuff in here, aren't we? But also, between this graph here and the x-axis, we're talking about stuff in here. And it says from x equal negative 1, well, that's where negative 1 is right there, to x equal positive 1. So what we're really being asked to do is to find the area of a region that's not connected. It's actually two separate regions, isn't it? And one of the regions falls below the x-axis, and the other region falls above. And so what we ended up doing here is adding a negative area on the left to a positive same amount area on the right, and so it looks like we have no area whatsoever. So what we're going to have to do is to break this up into two pieces. And what I mean by that, we need to find the area of this region. We'll call that A sub 1, that area, and we need to find the area of this region. And so the area that we're looking for is going to be the addition or the sum of those two areas. Now, the area of the region 1, okay, is an integral from negative 1 to where are we stopping? See, here's where the way we're looking at this. We've got a representative rectangle here. But that region just goes from negative 1 to 0, doesn't it? So we're going to look at those little rectangles from negative 1 to 0. Okay, that's going to be for area 1, negative 1 to x equals 0. Now, of course, in this case, since the y values are all below the x-axis, then we need the negative of those x cubes. See, the x cubes there are below the x-axis, so it's going to be the opposite of that amount, okay? And that's that negative idea that we see there, times the dx, which represents that infinitely small width, doesn't it? Okay, so we can calculate that area quite rapidly. That the integral of negative x cubed is negative 1/4 x to the 4th, and we're going to evaluate that from negative 1 to 0. So that means first we're going to put a 0 in for x, and when we do, of course, that will just result, okay, just putting a 0 in, and then we're going to put a negative 1 in, so that'll be, and subtract, so it'll be a negative 1/4 times an x value of negative 1 to the positive 4 power. Now, as we let the dust settle here, in the beginning we have a 0. That's all 0. And then we have a negative of a negative 1/4 times a positive 1. Well, that's just a negative of a negative 1/4, which is a positive 1/4, isn't it? Now, region 2, so region 2 is the region we have right here. Now that falls above the x-axis completely. And so the y values associated with this representative rectangle are all positive y values, aren't they? Now the width is still dx, but the height is a positive x. I mean, it's a positive x cubed. All those y values are positive. So we'll integrate now. We'll start those rectangles at 0, where that pinched region starts. And we'll stop those rectangles at positive 1. And we're integrating x cubed with respect to x here. And so we can go through this fairly rapidly as well. The integral of x cubed is 1/4 x to the 4th, and we're evaluating that from 0 to 1. And so we first put a 1 in for x, and then subtract what we get when we put a 0 in for x. Of course, when we put a 0 in for x, all that's 0. And in this case, we just have 1/4 times 1 to the 4th power, which is just a 1/4. So the total area, if you will, the area that we're really looking for is not 0. It's the area of the first region plus the area of the second region, which is 1/4 plus 1/4, or 1/2 square units, not 0. Again, the lesson is we need to pay attention to what the region really looks like. And that might be a challenge all on its own. Okay, let's, I think for now we'll summarize this on the next page. And that is what the summary idea is: what happens if we have a region that is kind of split into pieces that we're trying to find the area of. Okay, here's the summary when we have regions that are partially above the x-axis, or part of it's above the x-axis and parts below. So let's just look at the general idea here. We've got some curve, and we really don't know what this curve is, what really is going on with this curve, but let's suppose something looks like this. So there's our curve. And let's suppose the x value that's out here is A. And let's suppose the x value that's right here is B. Now, if we were being asked to find the area of the region that is bounded by the curve and the x-axis, then we're talking about this area along with this area. And we recognize that this area is going to show up negative if we're not careful. Okay? If we're not careful, that area will show up negative. This area would show up positive, wouldn't it? Because it's entirely above the x-axis. But if we just integrate without paying attention, we'll have a big negative number plus a small positive number, and we'll end up with a negative. And that could be reversed. We might have a small negative area and a large positive area, and that's kind of the worst case scenario, because if we weren't paying attention, we'd get a positive area and we think we're right, but it would really be wrong because we're adding a negative and a positive. It just came out positive. So what we have to be concerned about is, where does it stay completely below the x-axis and where does it stay completely above? And we see that switch is at this value, and we need to know that value. See, we'll just say it's C, but we need to know it. So what we would end up doing is we would talk about area 1 here, and we would talk about area 2. And to calculate area 1, we would set up an integral that started at A but stopped at C. And if this is the graph of f, then remember we need the opposite of those y values, because these rectangles, if we use the y value associated with this rectangle, that's going to be a negative y value, isn't it? So we need the opposite of those y values with respect to x there. Okay, now to calculate area 2 over here, since it's all above the x-axis, then we just need to do a regular looking integral, except we're starting at C. See, we're starting these representative rectangles not over here to the left of C, but from C to the right. And so we'd start at C and go to B, And these f of x values are all positive, or y values, and so we don't need to worry about adjusting them with a negative sign. So the area that we're looking for then would be a sub 1 plus a sub 2. Or we could say the integral from a to c of negative f of x with respect to x plus the integral from c to b of just f of x with respect to x. So be on the lookout for this type of situation, but I think that you'll be in good shape now and you can handle it. Well, that ends our discussion about finding the area bounded by a curve and the x-axis.